Huge, slow targets. In 1941, battleships could fight other ships but couldn't defend against coordinated air attacks. In 2026, carriers can fight ships and some missiles. But multi-axis hypersonic salvos? That's a different story. The analogy is too perfect to ignore. Sitting ducks. That's what military analysts say in private. American carriers in a war with China would be sitting ducks. Giant targets in open ocean where satellites track them and hypersonic missiles hit before anyone can react. The price? The Navy spent over $25 billion on just 2 Ford-class carriers. Add development and repairs, and you're looking at $40 billion. $40 billion in ships that can be sunk by missiles that cost $15 million each. That's the money trap. No amount of spending fixes the fundamental problem. Defense always costs more than offense when the attacker chooses when and where to strike. And history is screaming this at us. Pearl Harbor wasn't just battleships dying. It was a paradigm shift. Military leaders missed that technology had changed naval warfare. They invested everything in the wrong weapon at the wrong time. 2026 may be when we realize we're making the same mistake again. Or when we finally learn from history. The question isn't whether carriers are vulnerable. They are. Overmatch confirmed it. The question is whether American military and political leaders have the guts to admit it and change strategy before it's too late. China is watching. Every exercise, every missile test. Every time an American carrier operates near Taiwan or the South China Sea, satellites track it, data gets collected, tactics get refined, the hypersonic arsenal grows, the USS Gerald R. Ford keeps operating. Crews work exhausting shifts. Engineers keep emails running. The Navy keeps betting billions that they can fix the technical problems and build effective defenses. Maybe they can. Maybe Helios works. Maybe long-range drones create an effective shield. Maybe new electronic warfare confuses hypersonic missiles. Maybe. Or maybe we're watching Pearl Harbor in slow motion. Maybe in 10 years we'll see 2026 as the turning point nobody wanted to admit. China? They're playing both sides. Building missiles that kill carriers while building their own carriers. Forcing America into bad choices while covering every angle. It's a chess game where they move 2 pieces for every American one. The Fujian launches. It sails. It projects Chinese power. Meanwhile, hypersonic arsenals expand. DF-27 gets upgraded. YJ-21 spreads to more platforms. The math keeps favoring the attacker, not the defender. This is 2026. Carriers no longer dominate uncontested. Technology has caught up and made them vulnerable. History doesn't forgive those who ignore the past. You just saw facts the news isn't connecting. The USS Gerald R. Ford, $13 billion, broken. DF-27 deployed December 26, 2025. YJ-21 operational February 10, 2026. Overmatch warning of critical weakness. 861 missiles for one carrier's price. Carriers are vulnerable. The Pentagon already confirmed it. The real question, do we act before a 21st century Pearl Harbor teaches us the hard way? This time, unlike 1941, we have warning. We know the threat. We know technology changed naval warfare. While politicians debate and admirals plan, the clock ticks. Every day, China refines multi-axis tactics, tests new missiles, expands satellite tracking. In modern naval warfare, being the biggest target may be the worst position. $13 billion doesn't buy safety when the enemy can sink you for $15 million. If this made you rethink naval warfare, share it. Want to understand the geopolitical angles mainstream media ignores? Subscribe and turn on notifications. When technology reshapes the power balance every month, staying informed isn't optional. It's essential. You think you understand what a blood moon is? The truth is far stranger than you'd expect. On March 3rd, we're getting a total lunar eclipse. The moon won't vanish. Instead, it glows a deep red, like the sky itself is bleeding. But here's the thing, nobody explains. If Earth is completely blocking the sun's light, why can we still see the moon at all? Let me show you what Feynman discovered. Think about what should happen logically. The Earth sits between the sun and the moon. Earth's shadow stretches out through space like a dark cone. The moon drifts into that shadow, and right then, all direct sunlight gets blocked. It's like flipping off a light switch. The moon should vanish completely, lost in the absolute blackness of space. But that's not what happens. During a total lunar eclipse, the moon doesn't vanish. It transforms. It turns this reddish-orangey color, sometimes with copper tones mixed in. It's a stunning visual event we call the blood moon. Stop and think about that for a second. If the sun's light is blocked, where's that red light coming from? What's illuminating the moon? Here's the answer Feynman loved to explain. That layer of air wrapping around Earth, roughly 100 kilometers thick, isn't just a protective shield. During an eclipse, it acts like a giant lens. Sunlight doesn't just get blocked by Earth's solid mass. Instead, it bends around the edge of the atmosphere. Picture Earth as a solid ball in space. Now imagine a thin ring of atmosphere wrapped around it. When the sun sits behind Earth during the eclipse, sunlight grazes that atmospheric ring at the planet's edges. And here's what's fascinating. The atmosphere bends that light, funneling it toward the moon. But here's the crucial piece. Not all light passes through equally. The atmosphere is selective. It filters. And that's where the physics Feynman loved to explain kicks in. The moon becomes a projection screen. It bounces back the light that made it through Earth's atmosphere. What we're seeing isn't the moon generating its own glow, but the result of that atmospheric filtering cast onto the lunar surface. Compare that to a normal full moon. When the moon's lit normally outside an eclipse, it gets direct sunlight without any filtering. You see that characteristic gray-white of the lunar surface. But during an eclipse, the only light reaching it is that filtered red light bending through the atmosphere. It's a dramatic shift. So what's letting the light get to the moon? And why red light specifically? To answer that, we need to dig into the mechanism Feynman explained so beautifully. Earth's atmosphere isn't just a passive barrier to light, it's an active filter, and the physical principle behind it has a name: Rayleigh scattering. This mechanism explains why the moon turns red during a total eclipse. Let's try a quick thought experiment. Imagine you've got a flashlight emitting white light. Now put a red filter in front of it. What do you see? Red light. The filter blocks all the other colors. The atmosphere does something similar, but way more elegant. Here's what's going on. Sunlight looks white, but it's really a blend of every color in the visible spectrum. Each color has its own wavelength. Blue light has a short wavelength around 450 nanometers. Red light has a longer wavelength about 700 nanometers. When that white light hits Earth's atmosphere, it runs into gas molecules: nitrogen, oxygen, and others. These molecules are incredibly tiny, much smaller than the wavelengths of visible light. And when light bounces off particles smaller than its own wavelength, something specific happens: scattering. But scattering isn't equal for all colors. Here's the elegant math as Feynman would put it. The intensity of scattering is inversely proportional to the fourth power of the wavelength. What does that mean practically? Imagine you're in a packed room shouting something. Now imagine the people closest to you are like blue light, and the distant ones are like red light. The shorter the wavelength, the more scattering happens. It's like the nearby people hear and pass on your message in all directions, while the distant ones just let it through. Let's put some numbers on it. Blue light, with its short wavelength, scatters roughly 16 times more than red light. 16 times more. That's massive. That's why blue light dominates when you look up at the sky during the day. But during a lunar eclipse, we care about the light passing through the atmosphere, not the light scattered toward us. And here's the twist. Because blue light scatters so heavily, it gets knocked out of the beam crossing the atmosphere. Blue light bounces away, scattered everywhere by the atmospheric molecules. Red light, meanwhile, with its longer wavelength, doesn't scatter nearly as much. It glides through the atmosphere pretty easily. It's like the atmosphere is a color filter, letting long waves through while blocking short ones. Think of the atmosphere like a giant prism flipped backward. A normal prism splits white light into colors through refraction. Earth's atmosphere does something similar through differential scattering. It takes the sun's white light and splits it up, letting red and orange light pass through the thick part of the atmosphere. That's Rayleigh scattering in a nutshell. It's an elegant mechanism governed by a straightforward math relationship between wavelength and scattering intensity. And during a total lunar eclipse, this mechanism goes full force along Earth's edge, filtering the sunlight that reaches the moon. The atmosphere doesn't just filter, it also refracts, bends the light rays. Think about a swimming pool. Stick a pencil in water and it looks bent, right? That's the water bending the light. The atmosphere does the same thing, but on a planetary scale. That means light that should be blocked by Earth's solid mass actually bends around the planet through the upper atmosphere layers. Stop here for a moment. Let that sink in. The atmosphere is doing two things at once: filtering and bending light. It's like a red lens focusing red wavelengths toward the moon and Earth's shadow. Feynman loved this kind of explanation because it shows how one simple principle, wavelength-dependent scattering, creates a complex, visually striking phenomenon. No magic, no mystery, just basic physics at work. Here's the thing. This same mechanism happens constantly around you. Just look up. Why's the sky blue? Same physics. Blue light scatters 16 times more than red, so it bounces everywhere and floods your vision. What about sunsets? Why does the sun turn red, orange, sometimes pink near the horizon? Same physics, different angle. Try this visual experiment. Hold your hand straight out in front of you. Now raise it straight up above your head. That's how far sunlight travels when the sun's overhead. Now extend your arm horizontal, pointing at the horizon. Much longer path, right? When the sun sits low on the horizon, sunlight travels through a much thicker band of atmosphere to get to you. Instead of going straight down through a vertical column of air, it's crossing through a much larger section of Earth's atmosphere. Over that long journey through air, Rayleigh scattering has way more chances to work. Blue light scatters and rescatters so many times that almost all of it gets knocked out of the direct beam hitting your eyes. What remains? Red and orange light, which push through that thick atmosphere with less scattering. Stop and think about what we just connected. A sunset is physically the same, physics-wise, as what happens during a lunar eclipse. The atmosphere filters, removing short wavelengths and letting long ones through. The difference is just geometry. At sunset, you're looking through the atmosphere at the sun. At a lunar eclipse, light passes through the atmosphere and bounces off the moon back to you. See the pattern? 3 things you observe all the time: blue sky during the day, red sunset on the horizon, blood moon during an eclipse. 3 totally different moments, all following the same physics. Rayleigh scattering at work in 3 different contexts. That's what Feynman loved to teach. Nature doesn't have special cases. The same rules apply at different scales, in different situations. Once you nail the fundamental principle, you can decode tons of observable phenomena. Look at what we just did. Started with a question about the blood moon. Found the answer in Rayleigh's scattering. Then realized the same mechanism explains blue skies and red sunsets. 3 observations, 1 principle. That's why physics is so powerful. You don't memorize random facts. You build from first principles. Then suddenly, you're not just understanding one phenomenon. You understand an entire family of them. He taught that observation matters. You can't just theorize about the universe. You have to look. You have to measure carefully. When you actually pay attention to what nature's showing you, patterns emerge. Feynman loved challenging students to think this way. He'd ask, "See this everyday thing? Now question it. Why does it happen?" And when you dig into the explanation, what else can you explain with that same principle? This turns passive observation into active investigation. That was Feynman's genius. It's not about memorizing that blue light scatters more than red. It's about building intuition for how nature works. It's about spotting patterns. When you understand that, something shifts. You see the world differently. Phenomena that seemed random suddenly fit together into one coherent web of causes and effects. You develop what Feynman called a look for nature. You don't just see what happens, you see why it happens, and that's deeply satisfying. So picture this. March 3rd. The moon starts turning red in the night sky, and you'll know exactly what's happening. You'll picture sunlight hitting Earth's atmospheric edge. You'll imagine air molecules scattering the blue light away, leaving only the red light to get through. You'll see that red light bending through the atmosphere, hitting the moon in shadow, bouncing back to your eyes. It's not strange, it's inevitable. It's the predictable result of simple physical principles, and there's something beautiful in that. Nature doesn't need mystery to be wonderful. Clarity can inspire you just as much as mystery.